Hello everyone, in this video I'm going to show you how to design a common gauge amplifier. The terms commons means ground. Common gauge means grounding the gauge. So to do that, of course you cannot connect the gauge directly to the physical ground. If this case is the case, the circuit will not perform. It will not work. So what you need to do is to ground at the AC frequency. To do that, what you need to do is to keep a capacitance with large capacitance value, say 1 micro, and then you connect it to either the physical ground or to the AC ground. So this is the AC ground. The next thing that you are going to do is to use. Now first, let me explain. To begin with, we are going to use the biasing circuit that we have already done in one of the video lectures. These biasing circuits will end me up with a decent bias that satisfies the condition of the cutoff and also the saturation condition. So if you simulate this for the DC domain, the DC operating point, so you will end up with a list of voltage, and you will find out the gate voltage is 4.8, the drain voltage is 7.2, and the source voltage is 2.79. The threshold voltage is 1.9. Yeah, we have body effect, so it's still 1.9, the threshold. So if I simulate this again, I can check whether it has satisfied all the conditions. First, I'm going to just check the cutoff frequency, the cutoff condition. So the cutoff is the gate to the source voltage, which is 4.8 minus 2.7. 4.8 minus 2.79. And the source voltage is the threshold voltage is 1.9. So I got 0.11 volt. So it's very small, but it is positive. So I have satisfied the cutoff condition. Now I'm going to I'm going to check for the saturation condition. For saturation, we need to make sure the drain to source voltage is greater than this value. The drain to source voltage is 7.2 minus the roughly 2.8. 7.2 minus roughly 2.8. So it's way much greater than the gate to source voltage minus the threshold voltage. So I presume the saturation condition has been satisfied. Now, the next thing that I'm going to do now is to ground the gate. I have done it, and we insert the input. For common gauge amplifier, the input is going to be at the source. The output will be taken from the drain. So let's do it. So I need to add a coupling capacitor first. So this will be the source, the input, and I would add a AC voltage source. And the voltage source is around say 100 micro. We cannot use large value here. Now what I'm going to check is I'm going to add the output. So I'm going to use the capacitor to block off the DC, and then we add a low resistance here. The low resistance should be as big as possible. Let's say way bigger than this resistance, other one. So I will use 100K, and this is the so-called common gate amplifier. And I will use 1 micro for the input as well. And I will label the LED for the output. I will label it here. For the input, I will label it here. So this is input, this is output. So I don't need DC operating point analysis anymore. So I delete this, and then I will use AC analysis. Decade, and I put 100 as a number of points per decade. And the starting frequency is 100. The low frequency could be say 0.5 giga. So I presume it's almost done. So I save the circuit first, and you will end up with a waveform window. And in this case, you position your cursor to the waveform window and then right click, and you end up with a pull down menu, and then choose the option so-called add traces, and from there you plot the ratio of V out, V of out, and to V of in. So you get the band pass characteristic of this filter. So it's not too bad, right? You can also check the capacitance here, right? By increasing the capacitance or the ground, right? Maybe you will end up with better result. Not much better. Yeah, I think as far as I know, we have already achieved what we need. Okay. If you have any question, please leave your question to the comment section. Okay. Anyway, thank you for your attention. By the way, I think here I suspect that you can increase the capacity here to improve the bandwidth. Yeah, exactly. Because in Thevenin analysis, the voltage is equivalent to a short. And now instead of going through the resistive branch, you go through the capacitance branch. So if you further increase this capacitance, then you will further widen the bandwidth. This is the capacitance connected to the source of the transistor. Okay, so this is the way here. If you further make it 100 micro, then you get almost all the bandwidth. Okay, so this is the trick. Yeah, you can increase the capacitance here in a way to widen the bandwidth. Okay, I hope this helped. Yeah. If you have further questions, please leave your comments. Leave your question to the comment section. Thank you. Bye bye.